Hello everyone, my name is Angelique Tepan. Today I will be talking about torque and static equilibrium for my Module 9 laboratory experience. Here are the objectives that the students are expected to know by the end of this lab. The first one is identifying fundamental concepts like torque, moment of inertia, levers, and rotational equilibrium of rotational motion. Number 2 is analyze how distribution of mass around the axis of rotation affects the moment of inertia for rotating bodies. And number 3, applying rotational equilibrium to a system by playing with the applied clockwise and counterclockwise torques. This lab had 3 parts. The first one are the pre-lab questions, and just to see if the students can answer concept questions. The second one is the hands-on experiment, as we can tell. And the third one is a internet gaming activity to balance different weights. Now, these are part of the pre-lab questions, and the laboratory asked, what is a torque? Well, a torque is a force applied to an object floating around an axis. What is a moment of inertia? A moment of inertia is the rotational equivalent of mass in Newton's second law. And what is the right-hand rule of torque? The right-hand rule is a method used to determine the direction of torque an object faces based on the rotation. The rule goes, if we hold out our hand and we twist our fingers counterclockwise, this is my counterclockwise, we will see that our thumb faces up. Every time that a force is counterclockwise, the torque will be facing up. If it is clockwise, if it's moving like this, the force, then the torque will be negative. Now the students must identify the types of levers in each scenario. So, in this first scenario, this one, we see that the fulcrum is right here. We see that the load is right here, and we see that the force is right here. When the load and the force are on opposite sides of each other and the fulcrum is in the middle, this is a class 1 lever. Moving on, we can see that the fulcrum is once again in the middle, and the load is here, and the force is here. This means that this one is also a class 1 lever. Now this one, a hockey stick. We see that a person is holding this machine, instrument, lever. A person balances the entire system. So that means that the person is the fulcrum, is the center of balance. Here, or more like here, in the person's arms, right there. I mean, the person's arms are right there, but the force exerted in the middle, and the load is at the end. When this happens, it is a class 3 lever. Here we have other examples. Starting with this first one, we see that it's a human body, right? And so we have a hip adductor muscle force, we have a body weight, and we have a joint force. Now, to me, how the body is depicted with this little black diagram helped me decide that this is a class 1 lever. Why? Because we can see, or we can identify that the body weight is the load, and so the hip abductor muscle force would be the force, and then the resultant joint force will be the fulcrum, the center of balance. So with that said, to me, this is this is a class 1 lever. Moving on to this, we can see that the hand is holding the machine, keeping it steady. That means that it is stabilizing the machine. And the fingers exert a force in the middle of the lever, and then whatever is picked up is the load. Meaning that if the fulcrum is at the end, and the force is in the middle, and the load is at the end, this means that this is a class 3 lever. Now, for the physical part of this lab, we have experiment 1 with a rotating ruler. I will read to you the description. In this experiment, I will demonstrate how changes in the position and amount of mass or moment of inertia of an object have a significant influence on the torque of or moment of force required to rotate it. So in event 1, it asks us to put one piece of clay on each side of the ruler, halfway between the axis and the end of the ruler. Here you have. We're supposed to hold it like this, and rotate it like this. So, I concluded that when the two pieces of clay were placed on each side of the ruler only halfway until the end, the person can feel the weight difference, but it's easier to move them down and rotate. To me, this is pretty easy. Now, once the pieces of clay were placed on each, see how it shifted from here to here, and from here to here. It goes a bit down. So I said, once the pieces of clay were set down, one can notice a bigger weight difference since they are placed on both extreme ends of the rulers. Now, in event 3, when two equal pieces of clay are on each end of the ruler, which looks like this, boom, and boom, we see that it goes down even more. And it's even harder to rotate. It's harder to change its position. So I just said that the weight can be perceived as heavier. It is heavier to move. It has a higher inertia. Now, when asked which event clay setup produced the smallest moment of inertia, I said the smallest moment of inertia experienced was definitely the moment where the clay was put closer to the fulcrum, which in this case is my hand. This is because as objects are placed closer to the center of balance, their weight seems to change since the gravitational force is being redistributed. That's why it was easier to rotate. When asked which event clay setup produced the largest moment of inertia, I said the largest moment of inertia is produced when the clay is doubled at the end of the ruler. This causes the center of balance or fulcrum to feel even more mass. This is because as the objects are moved farther from the center of balance, the forces of gravitation work harder to distribute the mass. So that is why it has the largest moment of inertia. Now, what is rotational equilibrium? Rotational motion, and this I found in the manual, is when an object spins around an axis of rotation in a circular motion. Rotational equilibrium is when the object's angular velocity is equal to 0 and its torque is 0, meaning balanced. This is my level 1, which I scored 12 out of 12 out of. And this is my level 2, which I scored 12 out of 12 out of. That is the end of my presentation. Thank you for listening, and I hope you have a very nice day. Goodbye.